All right, so um, we've talked about automata, DFAs, and NFAs. We've talked about regular expressions, and that they all do um, whatever you can do with one, you can do with the other, right? In one case, we're accepting strings or accepting a language. On the other hand, we're describing the language, but they're roughly interchangeable. We also saw some limitations. We saw, for instance, that this language, where we have to have the same number of zeros as ones, that we couldn't describe in this way. We could not create an automaton or a regular expression to describe this language where n is an unknown value, right? Where n is just some maybe non-negative number. So that extra structure of having the same number of zeros as ones caused a problem. We couldn't resolve that. So let's take a look at a different approach. We're going to look at what's called a grammar. Okay, so a grammar for our purposes right now, we're going to modify this and change it a bit. But we will have four pieces to a grammar. We will have a set of variables. Again, we have an alphabet. The alphabet, sometimes called terminals. So it's the set of characters that we're working with. We again have a start variable. We're calling it S here. We might call it something different somewhere else, right? But just there is a variable that we are determining is the one that we're starting with. And then we have what's called a set of productions. Maybe we'll call that P right now. And these productions we might call transformation rules. These productions are in form like this. We're taking something from the set V, so the set of variables, and we're replacing that with maybe something else from the set V, or one of the terminals, and then some number of times. Okay, so this is kind of a formal definition that we will now put into, well, we'll look at an example, right? So we can see what we're talking about here. So this is like the idea of the MIU system that we talked about earlier in the term. If you have something, here's how you can create something new from it. Okay, so the set of productions or rules is similar to what we had with the MIU system. When you have something that looks like this, you can turn it into something that looks like that. All right, so for example, let's say that we have a situation like this. So what are we looking at? We're looking at the set of variables here is s. There's a single variable. Our alphabet. Our alphabet is 0 and 1. You can also think about the empty string here as being a possibility in terms of the terminals, right? So there are 3 things that you can convert a variable to and then not be able to do anything else with it. That's why they're called terminals, right? If you convert, well, actually, there's one final terminal, right? You can convert it to the lambda. So in this situation, the variable can be basically eliminated, or if you don't eliminate it, you turn it into 0s1. Does that make sense? So if you have a variable s, you can either completely eliminate the variable, or you can turn it into 0s1. So really, the only way to terminate the procedure, to stop, is by replacing s with lambda. Okay? And so our start variable is always going to be whichever one we've written in the top left. So it might not be called s, it might be called something else, but whatever we've written in the top left is our start variable. So in this case, the only variable is the start variable, and it's s. How many productions do we have? We have 2 production rules, right? You can do this, or you can do this. So what happens in this situation is we always start with the start variable. We start with s, and we try to see what can you create from there. What can you create from s? We could create the empty string, or we can create, let's change this. Start at s. We can create the empty string, or we can create 0s1. From 0s1, what can we create? From 0s1, we look back at the production rules and we say, well, we could eliminate the variable s, or we can create this by replacing the s with 0s1. From here, what happens? We eliminate, terminate the s, right? Replace it with the lambda. We get that. Or we can get that by again replacing the s with 0s1. Does that make sense? And so what do we have? We have this organized approach. And what does it look like we're building? What kind of strings are we creating? Look at the pattern of these strings. What do they all have?
The same amounts of zeros and ones.
Same number of zeros as ones, with all the zeros before the ones. Right? So this method of constructing strings allows us to, in a fairly compact way, describe strings that we could not describe with a regular expression. Right? So whatever we can construct, the set of things that we can construct with this is the language that we're talking about, right? So the language of this grammar is that set that we started with that we could not work with automata or with regular expressions. Does that make sense? This kind of grammar, where the variables are standing alone on the left-hand side and being able to replace them appropriately, is called a context-free grammar. A context-free grammar, the context-free-ish portion of that is corresponding to the idea that anytime you see an S, you can replace it. It doesn't matter what's around it. Now, if you think about our MIU system, when could you put a U onto the end of a string? Do you remember? It had to end in an I, right? So there was context to it. You couldn't just arbitrarily add a U to the end of the string. So that grammar or that structure was different than this. Not to say that we couldn't do the MIU system in this way. We don't know. But that description was not context-free. There actually was, you could only do certain things at certain times. Here, what happens anytime you see an S, you can replace it with the appropriate, with whichever piece you like. All right, so what's the idea? The idea is that we're going to utilize this we'll use this you will use this next term in compiler because you want to be able to see if something is formed properly. So there will be a grammar to describe something, and then you have a potential string. And we want to check to see, is this string in the language? So can we derive that string? Now with this particular grammar, deriving a string, what do you do? You just go down the tree until you have the right number of zeros, and then you terminate the variable. But what if there's lots of variables and maybe multiple ways to derive something? It turns out that the derivation will correspond to, or can correspond to, meaning. How you derive something can give the appropriate meaning. So what if there's two ways to derive something? What would that mean? There's two ways to derive something. That would mean that there are two meanings, potentially, for it, that are different, right? Two different derivations could correspond to two different meanings. So we will come back to this idea, but the idea of how you process something, giving it meaning. So some of you, I know, have seen there's also a version with 7 and a version with 9. But some of you have seen this sentence before. And if you've seen it, you know that there's a way to interpret, at least one way to interpret it so that it's meaningful. And there's actually potentially multiple ways to interpret it so that it's meaningful. Okay, so we'll come back to that sentence a little bit later on and look at it. But I want to look at this sentence instead. What does this sentence mean? The horse raced past the barn bell. That inflection. No, this sentence is perfectly correct. No missing commas, no missing semicolon. I mean, if we put a semicolon right there, then that sentence makes sense to all of us, right? The horse raced past, and then the barn fell. All right, but that's not the sentence that we're talking about. We're talking about this sentence. Okay, now, there is an interpretation that you probably don't know about, because the word fell does have like an old archaic meaning of like meadow. So in that context, okay, the horse raced past the barn meadow. Okay, but that's not the meaning we're talking about either. Right? We're talking about these words with the actual meaning that you are comfortable with. So what fell? What fell? There's only two nouns in here, right? The horse and the barn. Which one of them fell? The horse or the barn? The horse? The barn? Nothing? Something fell. All right, so what happens here? There's structure that it just doesn't feel right? There's something, it's like, wait a minute. When we get to that, when I read it out loud, I intentionally read it in a way that you can't tell where the separations or what's going on, right? Because just kind of reading the words, the horse raced past the barn, we do not expect the word fell to come next. Okay, so let me write down a sentence that has exactly the same structure, but so each character or each word that I write is going to match the structure of this sentence. All right, so let's see here. What about the car? We need a verb here. So what about the car driven? We need a preposition. Driven through we need a noun here, the intersection. And now we need a verb here as well. Does that sentence make sense?
The driven throws me off. Car driven.
The car driven through the intersection crashed.
The car, yeah, okay, never mind. I think it makes sense.
Right?
Yeah.
So what happens? It's all past tense, right? It's all someone else was doing the driving. The car wasn't driving itself, right? So someone was driving a car through an intersection. What crashed? Did the intersection crash? No, the car crashed. Right? That sentence makes sense. Now let's look at the structure. The structure is exactly the same, right?
Yeah.
So what happens? Someone was racing a horse past a barn, and the horse fell. Does that make sense? English is weird. But even in this case, because this word has multiple meanings, there are multiple ways to interpret this sentence. Because with this extra meaning of the word fell, the horse didn't fall down, right? The horse is still up and running. We just ran past a meadow somewhere. Without that version of the word fell, the structure is still there. So what do we have to be able to do, or what do we want to be able to do? We want to be able to take things and interpret their meaning. And one way, in certain contexts, that we can do that is in terms of a grammar. So a grammar provides the structure, and then we will be able to do some things that we can't do with automata or with regular expression. So we can describe things and construct those. And so a context-free grammar, and then the corresponding language is called a context-free language. And so we will talk about a context-free grammar and separately a context-free language. All right, the language is the set of strings that we can create with a grammar. And so context-free languages are, it's a different set than the set of regular languages. All right. So what about, well, okay, so we will look at the other languages that we have been able to create in the past and see if we can create all of those. So all of the regular languages that we could work with, can we still build those with a grammar? And then are there other languages other than just this one that we can build with a grammar? So let's see if we can construct the set of palindromes with a grammar. So what is the set of palindromes? What does the set of palindromes look like? Well, if we start with S, so I guess we could call it P now as our variable because that would represent palindrome. But let's say that our characters again are 0 and 1. And we are also allowed to use the empty string to eliminate a variable. What does a palindrome look like? Same forward and backward. So can we construct the set of palindromes using this grammar idea? So if you had a palindrome, so we had some particular palindrome, and we wanted to expand it to a bigger palindrome, what would we need to do? I mean, this palindrome is just a binary string, but we need to put the same thing on both sides, right? So we need to put either a 0 on each side that will expand to a bigger palindrome, or we need to put a 1 on both sides to expand to a bigger palindrome. All right, so what can we do? We can use that idea to say, well, let's replace S with zeros on both sides of the variable. What does that mean? That if we have a palindrome, it will grow into a bigger palindrome. Is S a palindrome to start with? Well, it's a variable, so it's not. But what if you had nothing? Is nothing a palindrome, an empty string? Well, it reads the same forward as backwards, right? So kind of by default. But we really want something there. And so we're not asking it's S itself, but the idea is this won't break the palindrome structure. All right, so what else could we do? We said we could replace this with 1s on both sides. And so what we'll often do is instead of writing it like that, we'll condense that. So there's 2 productions and we just write it on one line because we're lazy, right? We want to save some paper or some space or whatever. So we'll often write it like this, even though it's 2 separate productions. How do we get rid of, to terminate, how do we stop to say, okay, now we're done, we've created our palindrome? We could replace S with the empty string. Right, so now what are we saying? Well, the empty string it's not a palindrome, so we will accept it as a palindrome. So is this the set of palindromes? So let's see what we can construct. If we start with S, what can we construct? We can construct the empty string. We could construct 0, S, 0, or we can construct 1, S, 1. from here, what can we construct?
0,
We can construct 0, 0 by eliminating the variable s.
sure. 0, 0, S 0, 0.
All right, so I'm putting the parentheses just so we can see what happened at that step. What else can we construct?
0, 1, S 1, 0.
Is that okay? Now we have a bunch of stuff that can happen from there as well, right? We have 3 things that can happen from there. Let's just look at this one. This can terminate here, or we can go through it all again with 3 more options. If we terminate this one, what do we get? 0, 1, 1, 0. If we terminated this, we got 1, 1. So what do we have? We have this. Terminate over here in 1, 1, and then a bunch of other things that can happen. What do we see about all of those, except for the empty string? They're all palindromes, aren't they? Is this all of the palindromes? Will this create all of the palindromes?
No, you're missing single digits 1 and 0.
Yeah, we're missing single digits, or we're missing something with this process. Can we construct this palindrome?
No.
No. So we can't construct that palindrome or that one.
You also can't create 1, 0, 1.
Can't create 1, 0, 1. What else can we not create?
Any string with a single digit in the center.
Right. So we can't create any odd length palindromes with this. We can create, again, that's an even length, right? Length 0 is still an even length. So all of these that we're creating here have even length. How can we create an odd length palindrome? What would we have to change in order to be able to create something like this?
Allow S to be 1 and 0.
Yeah, we could also allow the possibility to add to the terminals, to replace S with 0 or 1. So now then, lambda, 0, and 1 are actually terminals. They're actually ways to stop the process. Okay, so then what happens? Then here, rather than just having these 3 possibilities, we also create the possibility of 0, 1, 0. We also create the possibility of 0, 0, 0. Right? So 2 additional strings that are created here. So we can terminate at that stage with this. We could terminate with this, or terminate with this. And so what does this do? This grammar then allows us to concisely, with 5 production rules, describe the set of palindromes. Something that we could not do with a regular expression or with a DFA or an NFA. All right, so what's to come? We'll be looking at grammars, seeing how to use those grammars, what we can do with them, and just as importantly as what we can do, what we can't do. So we're going to mimic over the next week or so, week and a half, what happened with automata. We will look at how to use these to achieve certain goals, and then what the limitations are. So there is a pumping lemma for grammars as well. So we will look at a way to determine, oh, you can't do this with a grammar, but you can do this thing instead. All right.